Okay, I think we can get going. So welcome everyone to this session on Nowcasting. We'll have 4 presentations today. We'll have Paul on Nowcasting GDP using VAT returns in the UK. We'll have Alessandro on Nowcasting monthly GDP with big data. Stef on timely earnings indicators, and myself on our Nowcasting approach at the Bank of England for UK GDP. Just a bit of housekeeping before we get going. Just a flag, all presenters have 20 minutes to present their work, and there'll be 10 minutes for questions after. If people have questions, please do use the Q&A facility at the bottom of the screen to submit those. And if you're invited to ask a question at the end, we'll enable your microphone automatically. And when we do so, please introduce yourself by stating name and affiliation. And the final thing, just note that the session will be recorded. And with that, I'll hand over to Paul for the first presentation. Paul.
Thank you. I'm going to share my screen. So I'm going to present some work I'm doing with Martin Weale on nowcasting GDP in the UK using value-added tax returns. So it's some work we're doing in close collaboration with the ONS. So currently the ONS publish a monthly GDP figure. It's an output estimate, which is the earliest estimate of the UK. And in order to compute this estimate, the ONS uses a monthly survey, the monthly business survey, which collect data on business turnover. And turnover is the proxy for output in the market economy. But we can also find turnover data in the VAT returns, because when firms submit their returns to HMRC, which is the department that collects the VAT in the UK, they also have to indicate their turnover for the period in question. So with the VAT, we have an alternative data source, and what Martin and I have been doing is trying to find methods to make use of this data. So what are the pros and cons of using the VAT compared to the MBS? So being from an administrative nature, the VAT, the sample of the VAT is much larger than the sample of the MBS. So in the UK, all firms with a turnover greater than £85,000 have to submit a VAT return to HMRC. On the other hand, the MBS is it's a census for large businesses, so it covers all large businesses. But for small firms, it's a survey. So by using the VAT data, we could potentially get more precise estimates, but also it will allow for regional analysis of turnover. So that's the 2 main advantages of the VAT data. There are 3 problems to solve in order to make use of the VAT data. The first one is the frequency. So the monthly business survey is a monthly survey, and now the ONS publishes monthly GDP. But the VAT data, takes the form of rolling quarterly figures. So when firms start submitting their returns to HMRC, they can start submitting in any month of the year. And then after that, they submit once every 3 months. So this creates 3, what we call staggers, so 3 quarterly patterns. So for instance, in stagger 1, it's the calendar quarter. So in March, firms will submit the turnover total for the period January to March. And then in April, we'll have firms submitting their quarterly total for the period February to April. And in each of those staggers, we have around one third of firms. And in order to make use of the data, they are grossed up to represent the entire population of firms reporting VAT. So in March, we have a number which represents a quarterly number, which represents all the firms reporting VAT. So at the end, we have a rolling quarterly series. And in order to publish monthly GDP from those, we need to interpolate the monthly pass in the data. So it's a temporal disaggregation problem. That's one problem. Then the second one is the timeliness of the data. So it takes about 6 weeks for the ONS to publish the monthly GDP figure using the MBS. But 6 weeks after the end of the reference quarter, there is only a small number of, a small share of firms who have submitted their VAT returns. So in this graph, we can see that 2 months after the end of the reference quarter, there are about 20% of firms who have submitted their returns. And so if we want to publish a timely estimate of GDP, we need to forecast the late returns using this 20% of firms. So it's a forecasting or nowcasting problem. And thirdly, while the MBS data are relatively clean because they can be cleaned manually, the VAT data are much more noisy. So here, it's a graph for the transport industry. So we can see that there are very large outliers. And so we need to find a method to spot these outliers and either disregard these observations or downweighting them. So it's a cleaning problem. So Martin and I have developed a state space framework when we can carry out the three problems simultaneously. But because of the magnitude of the noise, we also use a nonlinear method in order to clean the data. So we use a combination of cleaning methods. But the main model is a state space model where we can temporarily disaggregate the data, nowcast the figures, and also clean them. So for this, we model 11 releases of the VAT data. So Y1 is the VAT data. And so this is the revision triangle. So as we go to the left, the data gets more mature. So it's also missing. So and then we also use a covariate. So something that I forgot to say is because the MBS is a census for the large businesses, and also it's more timely than the VAT data, it will remain because there will be no advantage from using the VAT data for the large businesses. So what we do is that we use the MBS series for the large businesses as an indicator series or covariates when we carry out the estimation for the VAT data. And so it's a multivariate model. We model 11 of these releases together with the covariates. So that's the equation for the VAT data. So J represents the release and Y tilde is the signal. So what we interpret as the clean turnover, and RT is a measurement error. And what we do is that we split the measurement error between a bias, which is specific to each vintage, white noise error, which is also specific to each vintage, and then what we call news. So news is the accumulation of errors across vintages. So for better representation here, so the first equation is the equation for the most timely estimate of the VAT data. And the feature of the news here is that as the data gets more mature over time, the noise in the release decreases. So we get more precise estimates. So that's the observation equations for the VAT data. And so the Y1T here is a quarterly figure. So we need to temporarily disaggregate it into monthly figures. And also, since we use raw VAT data, the data are not seasonally adjusted. So we need to seasonally adjust it as well. So we model the data in logarithms because then we can account for multiplicative seasonal effects and also for heteroscedasticity. But since we have a temporal aggregation problem, so what we model XT is the monthly turnover. So since we observe quarterly turnover, we have to aggregate it into quarterly components. But if these components are modeled as logs, then the sum of the logs is not equal to the log of the sum. So it's a nonlinear, it takes a nonlinear form. Gamma is the seasonal effect, beta is the Easter effect, and then we also have a stagger bias because actually there are more firms in the calendar quarter than in the other two staggers, so we need to account for that. So it's a bit cumbersome to work from a nonlinear method. So Tommaso Proietti has derived an algorithm where we can directly work from the nonlinear equation. But here, because we model 11 releases of the VAT data together, it makes the model a bit unpractical because it's too slow to estimate and too complicated. So in the first paper, Martin and I have derived an approximation in order to use a linear model. So here, it's a linear approximation of the first equation, but it gives exactly the same results. So because output is a variable that changes slowly over time, the approximation is very precise. But now because of the COVID crisis and the very big fall that it has generated, it might create a bit of approximation error. So we will need to investigate this when we have the data on the COVID. And then we also have an observation equation for the covariates, so the monthly business survey data. because it's a monthly data, we don't have this issue of temporal aggregation. So then we estimate the model using state space methods. So I'm going to explain the model we use for the seasonally adjusted figure. So we use a local linear trend model where the seasonally adjusted figure are split between a trend and are composed of a trend and an irregular component. And actually, it's in this irregular component that we can make use of the MBS data, because we estimate that these components are correlated between the VAT and the monthly business survey. That's how we use the monthly business survey. Then to estimate this model, we use the Kalman filter and we derive the interpolant with the Kalman smoother. But because of the noise that I have shown earlier, we can get very odd results if we model directly this data. So one way to spot these outliers is to estimate the model and then analyze the standardized disturbances and do t-test on these disturbances in order to spot the outliers. But the state space estimation assumes that the data are normally distributed. But here, actually, most of the industries show more or less the same picture, where we have very big spikes, but never negative spikes. It's because we only analyze small and medium-sized firms. So for instance, if a firm makes a mistake in its return and let's say reports a turnover of 1,000 instead of a turnover of 10,000, this will not have a big impact on the series, because then when we aggregate all the firms, this will disappear. But if a firm reports a turnover of 1 million, then this will have inevitably a big effect on the aggregates. So the measurement error are most often positive. So it introduces non-Gaussian features in the noise. And so it doesn't work very well if we use t-test. So what we have done is that we use a nonlinear method or score-driven method. So they are called GAS or DCS. And they are very close to state space model, but then we can break free of the assumption of normality of the data. And so we set a model very similar to the state space model, but we assume that the prediction error VT can come from any kind of distribution. And here we're using a student T distribution where the degrees of freedom can be different for each tail. So it's very important, because then we can capture the very large error in the right tail of the distribution, but not in the left tail. Because for instance, with the COVID crisis, we can expect to have an outlier, a negative outlier, but this represents the true value of the data, whereas the positive outlier do not. So here, if we say that negative values are normally distributed, but positive values can follow a student T distribution, that's very helpful in order to clean the noise from the data. So we use these two methods. So we estimate one series using this nonlinear method and another series using the normal state space method. And what we do at the end is that we combine both approaches. So I'm showing the results using the transport industry as an example industry. So on the first graph, the graph 1, we have the initial data. So we can see the very large observation error. Here I'm showing the 11 successive releases of the data. In the second graph, I show the data after the cleaning using the t-test approach. And in the third graph, I show the data after the DCS cleaning. And then in the fourth graph, I compare the last release. I compare the result we get from the DCS with the result we get from the t-test method. And what feature we can see, so the solid line is the DCS method. We can see that it downweights some observation which are not spotted as outlier with the t-test approach. So when we want to use results from different models, one way to do so is to use a Bayesian averaging method, but this makes use of the log likelihood of the data. Here the problem is that we modify the data with the cleaning. So at the end, we cannot really, because the data is different, we cannot use the log likelihood as a comparison metric or as a scoring metric to average the models. So what we do is that we simply use unequal weights for both approach. So we perform the estimation at industry level, and then for each industry we estimate seasonally adjusted figures, which we aggregate to get the figures for the entire economy. And so here I'm analyzing the revisions. So what I'm doing specifically here is I'm comparing the 11th release, which we consider as the last release, with the earlier releases, so from 1 to 10. And then we are analyzing the behavior of these revisions. So the first 3 rows look at the revisions to the aggregated figures. And so we can see that the average, so one feature is that as the maturity of the data increases, we get more precise estimates, so the revision decreases. So that shows that the model works relatively well. And also another interesting result is that the average is producing better results than either of the 2 methods. So but by averaging, we get lower revisions. So the first 3 lines are the revision and aggregates, but because industries have different weights on the total GDP figure. So for instance, series like the transport industries have larger weights than most of the other series. The behavior that we see here could come from only a sample of like a handful of industries. So in the last 3 rows, what we do is that we analyze the revision at industry level and we disregard their weights. And we can see that, so because we analyze absolute revisions, they are inevitably larger than if we aggregate them first. But the important thing is that the revision also decreases as the data gets more mature over time. Here I'm showing the first estimate with the 11th and final estimate of the economy-wide figure from June 2014 to late 2018. And on the bottom graph, we can see the revision. So the revision is never larger than 1% and never lower than 1.5%. So on aggregate, the revisions are small, and it's also the first estimates. So it's the most noisy estimate. So on average, that's good. That's it. Thank you.
Thank you, Paul. I think we've got a couple of questions already. If other people have questions, again, just to remind you, please add them to the Q&A facility at the bottom of the screen. Then we can kick off with Anna.
Okay, I think you can hear me. So I really like the way you use the positive deviation to figure out when it's an outlier, when it isn't. But can you use the fact that you have data on many different sectors? So I didn't really got it whether you're doing, getting an aggregate or if you getting your estimate sector by sector, so you could look whether the outlier would occur at the same time for all sectors.
Yes, so we do the analysis at the industry level. It's true that we could use the comparison across industries. For instance, maybe if there is an outlier in all the industries, then probably it's an outlier that has an economic meaning. Mm-hmm. But it's a bit difficult to analyze all the industries together because we already analyzed 11 releases per industry. Then if we analyze the entire economy, the model will be quite big. But it would be definitely helpful in order to spot the noise from observation that have an economic meaning. Yes.
I'm not sure I got all your revision terms. You have many in the model, right? Can you identify all of them? It's not only 10. You have more than that, or I'm mistaken?
We are using 11 releases of the data.
And you have like 11 of those XC. And then you have this epsilon as well. Can you get the epsilon disentangled from the XCs?
Well, we can identify the epsilon compared to the XCs because the XCs, they affect all the, so for instance, the news which affect the last release will affect all the releases before, but the noise specific to the last release only affect the last release. So that's how we separate between the two components.
Okay, okay, thank you.
Thanks, Paul. I had one or maybe two myself while we wait for other people. From a more practical standpoint, I suppose, could you just explain how exactly this differs from what the ONS is doing currently in the way that they use these data, and how large an improvement might this represent?
To be honest, I'm not sure. I've not understood completely yet how the VAT data is incorporated into the output estimate, but it's not temporally disaggregated. Maybe it's divided by a third, but the problem with the VAT data is that it's so much noisy that you need to estimate this noise in order to get a precise figure. And to estimate this noise, you need to account for the specific nature of the data. So you need to account for this temporal aggregation. So that's what the model is doing.
Yep, got it. Thanks. I think there's another question from James Mitchell.
Hello. Could you say a little bit more about how your methods could facilitate the estimation of regional output, and if so, perhaps how the estimates produced by your method might compare with the short-term regional indicators that the ONS does now produce? Okay, so we have the access to the data. So the data Martin and I have access to is an economy-wide aggregate. So we don't have access to regional figures, but because of the nature of the data, because the sample is so large, then we could also do the analysis that we do on the aggregate. We could do it at the regional level. But then after, I can't really say I can't really compare with the method you're developing, because then we have not done the regional analysis yet. But I don't think something for future work. That would be good.
yes, I think, because you in the original analysis, you're not using VAT data, are you?
No, we are not. Hence my question. I'd be very interested in if and how we could exploit the sort of data you and Martin are looking at within our framework.
Yes, I think that one of the main advantages of the VAT data will be the regional analysis, because then the noise makes everything a bit more complicated. But if we can get regional estimates out of those, that would be really interesting.
Yeah, very good. Thank you.
And I think Martin Weale just wanted to come in on the previous question in terms of differences relative to the ONS's approach.
Yes, that's right. What I understand the ONS do at the moment, and I think they're using the VAT data only rather partially, that they assume they accrue equally over the 3 months of the return. And no, the methods that we've been using, that we've been developing, are very different from those. But no, without wanting to obviously put words into the ONS mouth, they have been taking a great deal of interest in the work that Paul has done, and have been crawling over the programs very carefully, with a view, I assume, with a view to using them in some form if they're happy with them. Could I also say something on James' question about regional data? There is an issue of attribution. The output data are compiled on the basis of establishments. The VAT data may relate to multiple establishments. You can have a firm, for example, that produces in more than one industry. The ONS do allocate the VAT figures between the industries before they give us the data, on the basis of the employment data that they have in the IDBR, and they could presumably also do that for regional data, where you have one VAT return that covers businesses in more than one region.
Thanks, Martin, and thanks, Paul. I think there are no more questions at this stage. I can flag now that if people want to carry on the conversation or pick something up later, there is a facility for that. It's called, can someone remind me what it's called?
The lounge.
The lounge it's called. So keep that in mind. Moving on, I think, to the second presentation, Alessandro, if you're able to kick off a couple minutes early, is that okay?
Yeah, you can hear me?
I can now, yes.
Okay. Good afternoon to everybody. Okay. Yes, you can see me now.
Yeah.
Just that I want to share my screen. Why? Yes. Why doesn't? Okay. I hope that you can see my slides.
Yeah, I can see them, Alessandro, yeah.
Yeah, you can see, okay, yeah, of course.
Yeah.
Yeah, because, you know, okay. Welcome to everybody, and just a few words to thanks the organizer to give us the opportunity to present our research here. Anyway, the paper that I'm going to present today is a paper joined with Tommaso Proietti from University of Roma Vergata, and the paper is related to nowcast and forecast GDP by considering a very large data set of monthly economic indicators. And in particular, our idea is to propose a new methodology that from one end allow us to deal and to overcome the curse of dimensionality in a very easy way. And from the other end, to construct a model that allow us to solve also the critical issues that we meet when we want to nowcast and forecast GDP using higher frequency indicator like monthly indicator that are essentially related to the rugged structure of the data. The approach that we consider, that we propose, is a two-step procedure. In the first step, we use a bivariate model that is essentially based on a small-scale factor model. And then the idea is to consider just one indicator per time. In this way, we overcome the curse of dimensionality, of course, because we are just a very small model. And in the but the problem arises when we want to aggregate all the estimate that comes from each single indicator. And then this is the argument of the second step. We need a weighting scheme, a procedure that allows us to aggregate all the estimate that comes from the previous step. Then essentially our procedure, our methodology is how to say, is partially based on Euromind approach proposed by Tommaso in 2011, and essentially the estimation process is more or less the same. But what is different with respect to the previous approach is the fact how we treat the number of indicators. In the Euromind, the choice of indicator was quite subjective, in the sense that we need to choose a bunch of time series to include in the model. Here, instead, we solve completely this problem using just one indicator per time. That's basically the idea of the model. Okay. Of course, the problem of considering or nowcasting the GDP using higher frequency indicator or using a large data set of a higher frequency indicator is not new in the region, and there are several attempts that try to solve this issue. Here we report several references related to this to this problem. And what is important to mention here, how we put inside these references, and in particular we are in the middle of factor model. Okay, the approach of factor model, in the sense that we are considering a very large data set, but we are proposing a solution that is related to the approach of factor model, but is a little bit different. And in a few slides, you will see how this difference emerges. The model, let me formalize briefly which is our point. Basically, we are interested in to the conditional mean of the monthly GDP that is unobservable, of course. And what we assume is the temporal aggregation here that is related to YT, capital YT. And we assume that the quarterly figure of the GDP is basically the sum of the 3 months that compose the quarter. Okay, that's the idea. What we are interested in is the conditional mean of the monthly GDP conditioned to what we observe, the quarterly GDP, and also to the monthly indicator. Then we want to grasp information from those indicators. And let me stress a little bit the notation here. And as you can see, we have delta and delta y that are related to the release of the quarterly GDP and the monthly indicator, just to stress to the fact that essentially we have to face with a rugged structure that is related to essentially the monthly indicators. And suppose for a moment that we are considering the ith indicator, that is the industrial production. Suppose we are in January, then the observation that we have in January is related to November. And then we need to fill the 2 missing values that are, and then we need to produce a forecast for this indicator. Okay, and then we need a machine, we need a model that allow us to solve this problem. This is in the first step of our procedure. Okay, we are interested in the conditional mean, and we use the bivariate model for each single indicator that we are considering. Okay, but to get the final estimate of the GDP, we need a weighting scheme, and this is the argument of the second step. Essentially, we need to weight all the information, all the estimate that comes from each single model, and this is a classical problem in the forecast combination, essentially. And what we need is the optimal WI that allow us to produce the optimal estimate, the final optimal estimate. How we deal with this problem? We deal with using two different approaches. The first is related to the in-sample estimate that comes from naturally from the estimation process that we are considering, then from the likelihood of the model. And the second instead is related to the prediction performance of the model, and we call this approach the out-of-sample approach. Okay, the out-of-sample weighting scheme. Then we have, from one hand, we have the in-sample approach, and from the other end, we have the out-of-sample approach. Of course, we we investigate also the flat weighted scheme, that is essentially the simple average. That is a good competitor in this case. Let me introduce a little bit the philosophy that is behind our model. And I hope you see the picture, and our idea rely on the fact that the GDP lies in the space spanned by the common component of each monthly indicator. Then let me describe better the idea. The common component of the GDP is the rainbow or the psychedelic circle. Okay, we assume that there is that each monthly indicator share a common component with the GDP. Okay, for instance, look at the black circle where there is inside XIT here. Then in this case, you see we have that a large part of XIT is shared with the GDP, and this is the common component that they share. The outside of the circle, this part here, is the idiosyncratic component. But our idea is rely on the fact that in order to get the in order to recover the common component of the GDP, we need to aggregate using a weighting scheme, and this justifies the fact that we need to weight all the common component, all the component that arise from each single indicator that is in the dotted, you see. And this is basically related to the approximate factor model structure, but in a different perspective. Okay. Basically, the idea is the same. Okay. The only difference here is that here we are considering directly the estimation of common component of the GDP, of the monthly GDP, using the monthly indicator. Then that's the idea. Now let me move to the model that we are considering. The model that we are considering is classical in this sense, in this literature, that is the theoretical framework is related to the small scale factor model that was previously studied by Cristiano Morosawa or Proietti, Weale, and co-authors in Euromind. And the idea is that XT, that is the monthly indicator, and YT, that is the monthly GDP, is related to the common component KT, which is driven by the coefficient theta. Here we have also the idiosyncratic component related to the, of course, the monthly indicator and the GDP component. Then Here we have xi, y, I, t, that is essentially this part here outside the rainbow circle. Okay, that's our model. In order to identify the model, we need several restrictions to impose, first of all, we need to impose a structure for the common component, that is an ARMA process. Then we need to impose independence between the two idiosyncratic components. And also we need some restriction to the parameters related to the ARMA structure of the model and the ARMA structure of the model. Sorry. That's the idea. Okay. What is important here to mention is that here we have to impose we have to remember that we are considering the temporal aggregation. Okay. And we treat the model in this sense. Okay. In order to estimate the model, I said at the introduction of we use the same statistical framework related to the Euromind, and the idea is very simple, in the sense that as previously studied by Proietti and co-authors, this model here can be cast in a state space form. Okay. Once the model is cast in a state space form, and it is possible to estimate the model by considering the maximum likelihood approach, using essentially the prediction error decomposition performed by the Kalman filter. Then we recover the one-step and multi-step forecasting, their variances, and then at the end we are able to compute the likelihood of the model. And the statistical treatment of the model, the estimation, is quite standard. I don't want to stress too much because it is quite standard in this kind of literature, but if you are interested, I have at the end of the slide that report the estimation process. But what I want to stress a little bit is in the second step of the procedure, that is related to the weighting scheme of our model. And in particular, we are considering, as said at the beginning, two different strategies. The first is the in-sample approach, and the second is the out-of-sample approach. The first comes directly from the estimation process, that is the deviance that comes from the that delivered from the Kalman filter estimation, and we compute the weights that are proportional to the deviance. And here, as you can see in equation 3, we construct the weights that produce the final estimate proportional to the deviance plus a penalty term, and this approach is quite similar to we can say that is a Bayesian information criterion approach. Okay, like the weights are proportional to the BIC criteria, essentially. Okay, and then for that reason that we call this approach in sample, because we are considering the information that comes from the estimation. Now, if we move to the second strategy that is related to the out-of-sample approach, in this case, we consider the we compute the weights that are directly related to the real-time prediction error of the model. Okay, and in particular, we construct the weight in a way that we are considering just the weight, that are proportional to the their prediction error. Larger is the prediction error, lower is the weight that the indicator receives. Okay, the problem here, and that's the our second novelty of our approach, is that when n, the number of indicators, is larger than the number of is larger than the estimation sample, we have the problem that this matrix, the variance covariance matrix of the prediction of the real-time prediction error, is singular, is not semi-definite positive. And we need a solution for that in order to invert this matrix. And we propose the solution that was previously investigated for other problems, for Markowitz optimization portfolio, proposed by Ledoux and Wolf.
Alessandro, sorry to stop you. Just to let you know, you've got a little under 5 minutes now to go, if that's okay.
Okay.
Thanks.
I'm quite. Thank you. Let me say just the idea. Let me give you just the idea. We can estimate the variance covariance matrix by considering a shrinkage target, where the shrinkage target matrix F is some highly structured estimator for the variance covariance. Then here, what is crucial is the lambda, that when lambda is equal to 0, we get the sample estimation of the variance covariance. When lambda is equal to 1, we get the shrinkage target matrix. And this allows us to solve the issues related to the problem that arise before. Okay, I just move a little bit on, avoiding the technicality related to this approach. Essentially, we have two approaches: in-sample approach and out-of-sample approach for weighting the all the estimate. The data set that we are considering, we have 535 monthly time series from the Euro area, considering different countries like Germany, France, Italy, and Spain. We have different sectors, and we run a pseudo real-time experiment related to the period between 96 to April 2019. This is the composition of our data, and we try to balance all the sector. And of course, we have soft indicator, we have a hard indicator, we have financial indicator, and stuff like that. Okay, we try to simulate what normally happens in the policy making office, in the sense that we try to simulate the real-time experiment, and our exercise starts at the end of January 2006 and terminate to December 2018. We evaluate the forecasting performance using the root mean square forecast error, and we compare our model with different benchmarks, like the autoregressive, like the dynamic factor model, and like the MIDAS approach. We have three situations in which we are when we run a pseudo real-time exercise. We are in a small information, in a medium information, in a large information. Small information when we do not have monthly information relative to the current quarter from hard indicator like industrial production, for instance, January. In the second case, we have information from soft indicators relative to the second month, but we still do not have information relative to hard indicators. And this is the case in February, the second month of each quarter. And the third forecast is obtained by, I have to stop, no?
It's just to say it's 20 minutes now, but if you want to keep going for another couple of minutes, I think it's fine.
Yeah, just to give you the result and I go to directly to the conclusion. That's the the illustration. That's the result of nowcasting and forecasting. Forecasting performance. Yes, we have that a dynamic factor model with EM algorithm is a good competitor, but we have that our weighting scheme, the auto sample weighting scheme, is the best one, even though in some cases from a double Mariano test is not able to beat the dynamic factor model. But we have we got very interesting result, and what is important is that our model allow us to also to open the black box related to the big data. And just to understand better what I have in mind, here I report the cloud of the most selected indicator, and then we are able to distill the information that are from those large indicators. And yes, the conclusion is that what we found is that the auto sample approach is the best weighting scheme with respect to the in sample, and also with respect to the simple mean, simple average, sorry. From the interpretation of result, we have that timelines is that the timing of information is just important as the quality of the data. And the other point is that soft data like survey have a large impact at the beginning, first month of reference quarter, but after the hard indicator become very important. And we have also result for the direct and direct approach, but we will see the next time. Okay, thank you, and sorry for the delay.
No problem, thanks. We've got a question from Anna.
Yes.
Hi, Alessandro. Can you show me again that table with the results that have the forecasting results?
Yes. Oh.
I want to ask you something about that.
Okay. Yes, I understand that it was very quick.
That one, yeah, that one. What is this dev and dev 10, dev 30, dev 50? Is this the deviance?
Dev and yes, the deviance. Yes, the in-sample approach. Sorry.
And that's basically what I wanted to ask. If you remember well, Joshua Chan had the paper so deviance is a kind of information criteria type of measure, right? It's just that they say that there's some issues with models with latent variables, which is the case you have here. So I'm wondering if that could be an issue or it doesn't matter.
Yeah, the idea is that we use deviance not just for in order to how to say, let me say, the Kalman filter procedure give us direct this information, no? And the information deviance is in a way optimal in this sense. And we think that using this deviance as a measure for, as a measure for constructing the weight could be an optimal strategy. But the problem here is that what we realize is the fact that sometimes the deviance of the industrial production, when we consider industrial production, for instance, is the best one, no? Because industrial production is the one of the best indicator. But what we realize is the fact that in a certain period, essentially in the period of the sovereign crisis, if we consider a different scheme like the auto-sample approach, we are able to distill better the information that arise from the soft indicators. That is not in the case of the deviance. And then for that reason that we empirically start to investigate different approaches. Just, I'm not sure that I answered to you.
No, I understood now. This is an in-sample approach. You could use the out-of-sample. No. I think I understood. Thank you.
You're welcome.
Can I ask a quick one too, Alessandro? Just very intuitively, if it's possible.
Yeah.
Why, why in principle is the bivariate indicator by indicator approach better than the standard throw everything into the same model? Is it the the forecast averaging that you then do, which kind of gives an additional degree of flexibility, which in practice ends up being helpful, or is there more to it?
Well, the idea can be related to the target predictors, in the sense that here we are considering the bivariate model in conjunction with the each single monthly indicator. Okay. Instead, if you consider, let's say, classical approximate factor model, no, you are not directly estimate the commonality between the GDP and the monthly indicator. We are assuming that GDP and monthly indicator basically share the same component. Of course, even in the case of approximate factor model, you have the fact that different using the factor loadings, you have different degrees of importance of each series. And the idea here is that we can, that's our idea, we can recover the commonality by considering the weighting scheme. Of course, we don't know the optimal weighting scheme, no, is in the hyperspace, but we try empirically different approaches, and what we realize is that the weighting scheme that use the out-of-sample as we consider the using the correction proposed by Weale and Wolf is a good strategy. That's I hope I have answered to your question, but
that's great. I think we need to move on to Stef now, if you're ready. Great. Okay. Thanks, Alessandro.
Thank you. Thanks to everybody.
Cool. Thank you, Andre. Let me start by sharing my screen. Alessandro, if you could, yes, thank you very much. Cool. Hope everyone can see the screen. And yeah, hello. Thank you for joining me for this talk. I am Stef Garasto, and I'm going to present a piece of research from Nesta on evaluating a new earnings indicator using salary information from online job adverts. Let me start by mentioning that so this is very much a joint piece of work by the Nesta team, led by Jyldyz. This is the open jobs data team at Nesta, whose goal is to help individuals, organizations, and governments to take more informed labor market decisions. We do this in various ways, and data-driven research is one of these ways, one of the ways that we're working towards this goal, and this is where this research comes in. So the rest of the talk is going to be organized around these sections. So I'm going to introduce the motivations, the data sources, and the forecasting models we used, and then I will specifically focus on two sets of results. One is like, how do the earnings from official statistics compare with the salary and job adverts, and two, how well or with like how much variability there is when we forecast earnings across occupations and industries. So yes, perhaps it goes without saying about earning statistics providing valuable insights, like they are a very important part of the labor market, for example, to understand which professions are in higher demand. And survey data do provide a good amount of information about earnings and wages, and some of the statistics are informative, definitely, and also published at relatively high frequencies. However, there can still be a lag between when the statistics are collected and when they're published. And also, ideally, we might even push that relative high frequency to more than a month. And this is, and we're interested in like, what are the steps? How can we get there? Because yes, there is generally a large appetite for faster measurements of economic activity. Like ideally, what we would want is like the equivalent of the one-day delivery from Amazon Prime, right? And this is where new data sources, like, for example, job adverts, can help. There are new job adverts coming out every day, which means they can definitely offer the potential for increased timeliness. But they are a new data set, so it is quite crucial to understand its strengths and limitations in depth. And that's the main goal of this research, as also what many other organizations are contributing to. But specifically here, what we want to know is how and to what extent can online job adverts enhance the timeliness of existing official statistics on earnings. To do this, we looked at multiple data sets. So in terms of official statistics, we analyzed information on earnings coming from multiple sources, like the annual survey of hours and earnings, average weekly earnings, and the labor force survey. We used the first one to compare between two data sources, and the latter two were used for then when we moved on to forecasting. We also got some information from the 2011 census. Specifically, we had to use a crosswalk between occupations and industries for reasons that will be soon clearer. In terms of job adverts, our data sets consist of job adverts from Burning Glass. We have more than 51 million of job adverts, and these were collected between 2012 and 2018. Let me start by being quite clear about what are some of the main limitations of the salary data from online job adverts. First and foremost, some of the job adverts do not have salary range. I'm sure many of you have come across the competitive salary as opposed to an exact number. And also when the salary is present, it's not necessarily expressed as a one number, but it can be a range. And this range can be quite broad, like you can see from the figure that the extent of the range can go into the tens of thousands of pounds. Also, there are new job adverts every day, but they've not always been collected. Specifically in our case, our time series only start from 2012. And also there can be even more missing information from job adverts. And like while their advantages that they do combine lots of different pieces of information about the labor market in one place, sometimes one of these pieces will be missing, which is indeed a limitation. In this case, we're mostly interested in industry codes and occupation codes. And also when we do have the information, since it has to be extracted from by parsing the text, there can be mistakes. Finally, there's also the issue of compatibility. So what we'd like is to compare apples to apples, but there are some details to keep in mind. So the first one is that official statistics capture both part-time and full-time earnings, but salaries in job adverts are generally extracted and then converted to full-time equivalents. So we need to do an extra layer of processing to understand which ones of those are part-time or full-time. Also, job adverts do not have information about incumbent employees because they only represent new starters, like new vacancies being advertised, and then people being hired for that, which also means there is a lag in between when a job is advertised and when the person hired actually starts that job, and then that job appears on the payroll. The plus side of this is that it means that advertised salaries in a given month may actually be kind of a leading indicator of the salaries paid in several months' time. Despite all these limitations, there are positives, and well, one is that some of these issues will be less relevant over time in terms of collecting more and more data, improving algorithms to extract information from them, perhaps even like changes in industry practice in terms of pushing more and more towards advertising actual salaries and potentially with shorter ranges. And also at the moment we can actively take steps to mitigate some of these limitations. And lastly, the advantage, there are definitely advantages to using job adverts, even despite this limitation. They are a data set worth exploring. But yes, we do need to do some pre-processing, and we start here by, so I mentioned how the occupation might not always necessarily have been matched as accurately as possible, so we try to improve on that by using job titles, so clean job titles, also using the ONS index on job titles and trying to match those to occupation. Having done this, we could also have a measure of like the uncertainty, like how reliable those matches were, and we could filter out the matches that weren't as reliable as we wanted. We also removed some low-level occupation, like some of the unique groups that for which we didn't have that much data, like less than 675 observations between 2012 and 2018. And after this, we also filtered by the salary information, so whether it was missing or whether it exceeded threshold for extreme value, whether that was actually considering outliers, because sometimes that can happen when there are conversions from hourly rate to full-time equivalent, or simply being, for example, a mistake in the algorithm extracting the information. This left us overall with around 14 million of job adverts remaining. And the next step in this case is to correct for some of the biases. So job adverts can also be sometimes biased toward high-skilled professional occupations. And so to change this, we resampled the data set so that it mimicked the composition of employment by 3-digit SOC. Once all that was done, we could directly get the monthly average salary by 1-digit SOC. We kept it at the broad level since it was an exploratory analysis, and we wanted to like have a bit of an idea of like potential underlying patterns rather than going directly to increasing the detail of the occupations or industries analyzed. To obtain the similar time series for the industry, as mentioned, we had to use a crosswalk from occupations to industries from the census, and this was because matching job adverts to industry information was also like not, we didn't have a current match to use, and we're now also working on like algorithms to fill in those gaps. So for future research that can be changed. So yeah, the final outputs are multi-time series, which means we want similar outputs from the official learning statistics. So as mentioned, at least for forecasting, so annual weekly earnings and labor for survey are resampled to multi-time series, for example, for the LFS by interpolating, using a linear interpolation to get the monthly measurements, while we use the annual survey of hours and earnings to do a slightly different piece of analysis to assess how comparable the two data sets are, so official statistic and job adverts, and we use this survey because it is considered to be the UK's most reliable and detailed source of information on earnings. Again, because job adverts only have full-time equivalent, we use gross annual pay for full-time jobs at the level of unit occupational groups, and we do a year-by-year comparison over a period of 5 years. To make this comparison as robust as possible, we took the average absolute difference across multiple quartiles, so between the two data sources, and this is shown in the figure. So we take the difference between the values of the two data sources in the first quartile of the distribution of salaries, the difference in the median distribution of salary in the third quartile, and this is all done by occupation in the 4 digits subcode. And then we average, and then we normalize by the mean salary reported in the survey. The one thing I haven't mentioned is the reason behind wanting to do this comparison is that what we wanted, like our goal was to get a general sense of the discrepancies between the two data sources, so if one has to be used to predict the other. And also you kind of wanted to identify which occupations might be good candidates to do this forecasting. And yes, so the forecasting was the next step. And what we wanted to check was whether we could produce more accurate and timely estimates of earnings by using information salaries offered in job adverts. So we have our baseline is to forecast using only historical statistics, and then we compare this with the forecasting results using either historical statistic and online job adverts or job adverts only. The root mean square error was used to measure prediction accuracy over a forecasting horizon of either 1 or 6 months, specifically for the LSTM would be 1. And we split the data set into training and test. And here you can see a bit more details on the specifics of the model. So for the autoregressive, we use 2 different models. One is the autoregressive model. And we use different types based on whether the time series were co-integrated or not, as assessed by the Granger causality and augmented angle Granger 2-step co-integration test. We also conducted a bit of a grid search to choose the model parameters and included seasonal parameters because the time series, the official statistics we use are, and also the online job adverts are not seasonally adjusted. For the LSTM, so long short-term memory model, these are neural networks that are particularly well suited to process time series, and their main advantage is that they can potentially deal with non-linear relationships. They can take the non-linear structure in the input and use it to their advantage, but the downside is that they usually perform better the larger the data sets used, and we did have quite a small data set. So these initial results that can be improved over time. Again, we wanted to include seasonality, so we used 12 lags. We have 1 hidden LSTM layers and 1 dense output layers. Data standardized between -1 and 1. Again, we explored a bit in terms of network parameters and via a grid search technique. But the most important thing to mention is that we model the delay with which official statistics are published by dropping some of the data points. So specifically, we dropped the last 2 points for 2 months for the prediction of earnings by industry using the EWE, and the last 3 months for prediction using the LFS. Okay, so this is
sorry, just to flag, it's 5 minutes now, if that's okay.
Cool, thank you very much. So let me go ahead with the results. I'll start from the comparisons between official statistics and online job adverts. So you see from the figure that there are quite, the range of the results can be quite large. So some occupations differences are quite small, for some are quite big. So the average was a difference of 13 percentage point from the mean salary in the annual survey of hours and earnings, and this is across all of the 5 years. And the median was 10 percentage points, so 50% of the occupations are within 10 percentage point of the average of official salary. Also, we noted that online job adverts are likely to underestimate earnings for around 2/3 of the occupation. If we drill down a bit more and understand which occupations, let's say, did better on some level and which one did worse, these are the occupations that were most, whose salaries in online job adverts was the most aligned with the official statistics. And you can see there is a large, this span large set, and they include engineering, administrative, and financial occupations. And it's kind of similar for the occupations which are the least aligned. So they again, they're wide ranging and include social workers or postal workers, plant and machine operatives. What we wanted to know was, like, is there a pattern? Like, can we identify some features that explain which occupations are more or less aligned? So we did some exploration, and like one of the hypotheses was that, okay, if an occupation is small, then there would be greater level of noise in, well, both in the official statistics and in the online job adverts, and this would lead to greater discrepancies. However, this was not necessarily the case. Specifically, the discrepancies did not, it wasn't a smaller discrepancies if we increase the number of full-time jobs or the number of job adverts per given occupation. Similarly, it didn't appear to depend on which occupations had a higher average rate of change in earnings over time. So let's say more or less stable time series in a way. There are some more options that we would like to explore in the future. So one is the salary range. So the broader the salary range, the more likely it is that the final earning will be different from the mean of the salary range. And also an occupation scope. So some occupations are less defined, like, for example, management consultants and business analysts. The occupation includes more than 30,000 unique job titles even after normalization. This means that there are large intrinsic variation that can make that can lead more easily to discrepancies with official sources of data. In terms of the last part of this presentation, I'm going to focus on forecasting earnings. In terms of a bit of how that resolved is that we can do a bit better with LSTM. We can increase the accuracy of the estimates. It's not the same for other regressive model. They do perform a bit better than LSTM, but this might be just because of the dataset size. But the reassuring news was that the two time series, like job adverts and official statistics, are like, they do have a statistically significant relationship as measured by the ground causality test. So there is definitely potential to improve the estimates of earnings for occupations and potentially industries. So how did we do? So these are results, again, just for the LSTM, since this is where we see some differences for occupation. We can see for most of them, we do achieve some improvements, either by combining official statistics with online job adverts data or only using online job adverts data, although I have to caveat that for skilled trades occupation, this wasn't robust to changes in the normalization scheme of the data. So when we changed to normalize between 0 and 1, we didn't see the same results. And for industries, again, we see some improvements, for example, for accommodation and food service activities, financial insurance activities, but not for all. And again, some of them are not robust by changes in the normalization method. So I can see I'm 1 minute over time, but let me maybe take a tiny bit more time to conclude. So our question was, can we enhance the timeliness of existing official statistics using job adverts? And the tentative answer at this point is yes, but results so far are dependent on the specific occupations. And we can see this both when we compare directly with the annual survey of hours and earnings. So there can be either small or very large discrepancies. And also where forecasting earnings, job adverts seems to be beneficial for most occupations, but only up to 4 out of 13 industries. Overall, this might not necessarily be a surprise, since it is unlikely a new source of data will be a cure-all. It won't be necessarily a universally good or bad predictor of earnings, but it can help. And yes, more research is needed, but the more time it passes, the more data we collect, and the better we can do this forecasting. And yeah, in terms of future work, we want to try and improve, as I mentioned, we're working on algorithms to improve the per-processing stage, collecting more data, expand the parameter search for the LSTM, and also increase the forecast horizon. And finally, also try to do some more in-depth investigation of which characteristics might explain the discrepancies. Thank you very much.
Thanks very much, Stef. While we wait for others to post questions, I'm sorry, I think I missed the first minute or so of your presentation because my connection's a bit wobbly. You probably mentioned, but I didn't catch what the source for these data was. And I was also wondering, sort of in terms of operationalizing the, on a regular basis, getting the job ads data, how straightforward is that to do? Because you know, from a practical standpoint at the bank, this is a massive industry at the moment, trying to get a hold of as many you know, naturally occurring timely data as possible, and investigating to what extent that helps us forecast things. But obviously a challenge besides the many issues with data quality, because these aren't made to be indicators, is just, you know, how much of a burden it is in practice to get it to work. So if you could just say a couple of words on that, that'd be great.
Yes, so in terms of your first question about sources of data, so so far we've sourced, which also linked to your second question, so far we've sourced job adverts from a third party. So in this case, it was from Burning Glass. And this was 51 plus millions of job adverts, while yeah, official statistics are the 3 main surveys to forecast earnings. Yes, the point you raised is absolutely crucial, and we've been, Nesta, we've been exploring this issue for quite some time. And to be honest, I don't think it's easy to build the pipeline to collect job adverts. There are many third parties that are doing this, but this comes, well, A, at a fee, and also with the fact that they will have done some pre-processing to extract information, but usually with proprietary algorithms. So even not necessarily, even just not necessarily in terms of accuracy, but also like in terms of how to know, like how to get a bit more into the details of how the algorithm works to extract information from job adverts that generally not possible with sourcing from third-party data. But yes, Nesta, we do want to start collecting our own job adverts, and we've been working towards being able to do this. And also, I think LMI for All is also working towards a similar goal. So I think, even though up until now we're most reliant on these third-party companies, I think it'll get better and better, if that makes sense.
Yeah, thanks very much. There is a question from Anna.
If I understood well in your results, LSTM does better than some linear model. Is because LSTM captures nonlinearity? Is that the right intuition?
So so it's, rather than LSTM doing better than linear model, in this case, it's more that the LSTM with online job adverts data does better than the LSTM without online job adverts data.
I see.
And this is also with dropping some of the past months. So like, let's say 3 months before of information from the LFS, which we wouldn't have available if we were to, like, let's say, send this into more of a production stage in which we want to do it month by month, so past the testing phase. So this kind of tells us that there is information in the online job adverts data that can help us predict earnings from official data.
And why you thought was a good idea to use LSTM for this problem? That was
that is generally related to what you said before. Like, it can take advantage of nonlinear relationships, not just between one time series, but also between 2 different time series. And the same could be said of general neural networks, like just a formal neural network. But the LSTM is generally better at dealing with time series, so it does have an internal time loop that processes time series data, also including the relationship from one time step to the next. The disadvantage is that it generally needs larger data sets, but one thing that we want to explore is also to understand, okay, but how large does this data set actually have to be? A first thing that I can mention is that potentially in the future we could also look into combining 2 different models. So because the other regressive models, they also perform quite well. So it could be also an option to combine both nonlinear and linear models.
Yeah, you probably could do a layer of LSTM and do another layer with some kind of autoregressive. People are doing loads of combined models as well, and they've been shown to work in some cases. But it is an interesting use of LSTM.
Okay, thank you very much. I don't think we've got any other questions for now. As I said earlier, anything you can pick it up later at the lounge or just by messaging Stef directly. So I think we can move on now to the final presentation, and I'll let Paul do the honors of moderating the questions at the end. Let me just share my screen. Hopefully people can see the screen now. Okay, so what I wanted to do today is kind of give you a bit more insight into, sorry, 1 second. Okay, sorry, into our approach to nowcasting GDP at the Bank of England, and in particular tell you about the most recent tool in our toolkit, which is a new MIDAS-based model, which we've introduced in 2018. So that, to those of you who might be familiar with the old QB article that we published a couple years ago, describing our approach, that won't be covered there. So it's a bit of an update on how we're doing things at the moment. And I think it's also interesting in the sense that it's a bit of a twist on the standard MIDAS approaches, and it's one that's informed and very much geared towards sort of exploiting what we know about various relevant bits of data that we use for nowcasting UK GDP. And in addition to that, it's also a framework that in principle is applicable to a much wider set of variables, as long as you've got 2 things going on. So as long as your problem is one where on the left-hand side, you're targeting, say, a quarterly variable, but that same variable happens to be also sampled at, say, monthly frequency. So you want to exploit that. And you also have other indicators, say, in the case of this example, business surveys of UK output. So I'll tell you a bit more about that and the details in a second. Now, the background to this was very much linked to the ONS's change of their GDP publication model, where the ONS started publishing monthly GDP since June 2018, I believe. And alongside that, there were a couple of other related changes. So in practice, the main things that changed were the publication of the second, well, of index of services in general, which used to be published later than industrial production and construction, was brought forward by around 2 weeks. And so essentially completing monthly GDP together with those other output sectors. And at the same time, the first estimate of quarterly GDP was pushed back by 2 weeks. And so in practice, that resulted in a situation where we essentially, before getting the quarterly estimate of GDP, we would be able to see 5 of the 6 months of the monthly GDP data, whereas previously, the first estimate of GDP would be published together, essentially with the second month of services. So that changed things quite a bit, as I'll tell you in a second. And it also meant, from a bank-specific perspective, that the first estimate of quarterly GDP, which was usually published a few days before the inflation report, or what's now called the monetary policy report, it started being published after that. So it's quite important from certainly a reputational point of view that we get that as close as possible. And I did mention the old way that we used to do things. There's a 2018 article on that. And we used to have 3 models, a MIDAS model, a dynamic factor model, a bridge model, essentially time series based. And we kind of took a combination approach to that. But really, in practice, you know, the first 2, the MIDAS model and the dynamic factor model, were quite helpful with extracting the signal from things like, you know, soft indicators in general and the business surveys, such as the PMIs and so on. And that was really, to an approximation, all that mattered under the old publication schedule. But with a new one, that additional month of GDP and, you know, the obvious self-evident mechanical link between monthly GDP and quarterly GDP made that quite hard to ignore. And those models weren't really equipped to deal, or weren't at least specifically geared to optimally kind of dealing with that official data, and indeed the mechanical relationship between the monthly and the quarterly. So that made things a little awkward in that we had 3 models, and we have to say, well, we think these 2 are good for the first 2 months, but then monthly GDP comes out and we have to drop that because the data are what they are. So that in terms of explainability, that wasn't ideal either. So what we wanted to do was see, you know, can we develop a single framework which kind of, one, you know, efficiently deals with soft indicators and with monthly GDP, but also that kind of does this weighting across the data cycle with sufficient flexibility that we can be confident that we're taking the right amount of signal from each of these at different points in time. And we can easily explain the changes in our nowcast from saying, you know, our model was putting 30% weight on monthly GDP data up until yesterday, but after today, you know, it puts much more, and so we're changing our nowcast for that reason. And it turns out that the MIDAS framework in general is a quite flexible and convenient framework to exploit many of these properties of the data that we wanted to make sure that we're exploiting properly. So what I'll do here is illustrate that approach, focusing on an example just with top-down UK GDP, so keep it simple. Although actually in our day-to-day forecasting, we more often tend to run a 5-way output split, and that performs just as well. And you know, it's helpful from a storytelling perspective. So apologies. So just before moving on to the data, just a quick background on MIDAS models. I presume most people will be familiar with those. They're mixed frequency models. In plain English, what that means is just, as I said, you can have a lower frequency variable as a left-hand side, and you can directly use higher frequency lags on the right-hand side in one regression without the need to take averages or those sorts of things. And in addition to that, in its original form, the idea is also to have a model that's quite parsimonious, and so you can use potentially many lags of the higher frequency variable at a relatively low cost in terms of degrees of freedom. And the way that that's done is by essentially, tying your coefficient profile on those lags of the higher frequency variables to some known functional form instead of estimating all of the individual coefficients. So you impose some constraint on the shape that that can take, but you can estimate that by using up much fewer degrees of freedom. And to some extent, just beyond that, sometimes you just want to have a more restricted model to avoid, having collinearity issues and so on and so forth. So traditionally, that known function that I mentioned is the most popular one. Is probably the exponential Alman. That's really parsimonious. You only estimate 2 parameters, but it is or it requires nonlinear estimation, and that in practice can sometimes go wrong, and particularly if you start throwing more than one lags of more than one indicator into the same regression. So we're avoiding that. And what I'll do next is just quickly talk through a couple of other variants which are more estimation friendly, and which will be the ingredients that we're using in our framework. And so one is just still taking that restricted approach. So you're still using some parsimonious functional form. Is just the standard non-exponential Alman lag, which is just an additive linear polynomial, and you can rearrange the regressions such that you can just estimate that by OLS. So it's a relatively straightforward thing to use. It still gives you some degree of flexibility. So instead of say assuming taking a quarterly average where all your months get the same weight, you can still skew the weight towards say the most recent lags or older lags if you're using something like an expectations indicator or something like that. No problem. It does have a drawback, which is you do need to pick the number of lags and the order, the degree of that polynomial relatively carefully, because otherwise it can get pretty badly biased. But I think in our case that's not really a big issue, because we are quite familiar with these right-hand side indicators, the business surveys and so on that we're using. And we know that essentially it's something between 1 or 2 quarters worth of lags is what matters, and beyond that there's no signal. So that's not really a particularly binding constraint in our case, I think. Another limiting case is just do away with the restriction altogether and just estimate your mixed frequency regression by estimating individual coefficients for each of the monthly lags. And that's what's called unrestricted MIDAS. And in the literature, that's been shown to be quite competitive and potentially outperforms standard MIDAS approaches, particularly when the mismatch in the frequency between the left-hand side and the right-hand side variables is relatively small. So quarterly to monthly would be one example of that. So in macro applications, it's an approach that tends to work quite well. But I think that there are other data properties that matter too for whether or not how unrestricted versus restricted you should go. And I wanted to talk a little bit about those things now, as I just give you a quick bird's eye view of the data that we're going to use in this exercise. So this first chart here is just showing quarterly growth, quarterly UK GDP growth. That is your dark blue line, and the swathe is all of its former incarnations. So that's just showing you that these data get revised quite a bit. And indeed, in some periods, the dark blue line looks quite different from the pink line, which were the first estimates that the ONS published at the time. That's perfectly perfectly normal, and it's just part of producing economic statistics. But it does have some implications for forecasting and for model evaluation in particular. And that there's literature on this, and pardon. And when this is the case, it's quite important to use real-time data for your model evaluation. So all of the things that we're going to do from now on is using full real-time data. So, the first estimates of quarterly GDP, but also for the right-hand side variables, we're going to be using at each point in time what was available at that time before it got revised, potentially beyond recognition in some cases. So this is what monthly GDP growth looks like over time. So it's quite a volatile series. And a quick word, so this obviously isn't available in real time, published by the ONS going back before 2018, when the ONS started publishing monthly GDP, or calling it that at least, but the information that underpins monthly GDP was always published, so that wasn't really that fundamental a change beyond the labeling. So you can construct a very good approximation of real-time vintages of monthly GDP from aggregating up the real-time vintages of index of services and industrial production and where available construction, because that came a little later. But the key thing about the monthly GDP data, as I said, is how it is just mechanically linked to quarterly GDP, and that's a very important property that we want to exploit. Now, the other important source of data for at least traditionally forecasting UK GDP are these well-known business surveys of output. So things like the PMIs, the CBI surveys, and the BCCs. And here we're using the composite output balances. So that's just aggregating up the bottom-up surveys of the services sector and the manufacturing and so on, weighting them up by their respective GVA weights. And the thing I wanted to highlight here is how, the surveys look much more like the quarterly GDP data than they do like the monthly GDP data. So, one way to describe this is that they kind of track the broad GDP trends. But if you kind of overlaid this on the quarterly GDP data, it kind of struggles with some of the more volatile moves in quarterly GDP. So that's another thing to bear in mind. So what is it exactly that we do? This is the essential building block of the model. So it's this hybrid specification. It's a MIDAS regression where you combine two things in the same regression. So you include lags of your business survey, and at the same time you include lags of monthly GDP growth, and your target variable is quarterly GDP growth on the left-hand side. And I'm going to argue that the simultaneous inclusion of these things in the same regression is the key to the model's good performance that I'll show you in a second, because what it allows you to do is for the model to decide, and being a MIDAS approach, it has to be re-estimated at each point in the data cycle. So every time that there's a new data release, we re-estimate this again. So by having these two in the same regression, the model can decide how much weight to put on one versus the other in what should be an optimal way. So the other thing to flag is the lags of monthly GDP, we're using an unrestricted specification for that, whereas for the surveys, we're using the Alman lag restricted. So that's, and I'll say a couple of things about that now. So the reason that we're using the unrestricted approach for the lags of monthly GDP is very simple. It's that there is an extremely precise mechanical mapping from monthly to quarterly. And so you want to have an estimation approach that is sufficiently flexible to allow you to capture that. And indeed, the monthly GDP data are so volatile that you'd expect, you know, if there's this clear relationship, you'll be able to estimate it and recover that to a high degree of precision. And this chart here is just showing in broad terms what that mapping is. So, you know, these are months 1, 2, and 3 of the current quarter. These are months 1, 2, and 3 of the previous quarter. And you get this sort of staircase where month 1 of the current quarter gets the most weight. And the intuition for that is just in an all else equal sense, if growth in month 1 is higher by 1, then all 3 months are higher by 1 in a level sense. And so that boosts quarterly growth by that same amount. Whereas if you move to the second month, then the same bit of news only affects 2 months instead of 3. So the news is only 2/3 of that, and so on and so forth. So it's crucial if you want your model to take the monthly GDP data seriously, as it should. It's crucial that you specify it in a way that is able to capture this mechanical relationship. But when you estimate those coefficients, you know, you don't have the 6 months, you don't have the perfect relationship. So you have, say, 3 or 4 or 5, depending where you are in the data cycle. And so the coefficients will reflect not just that mechanical relationship, but that will be distorted in a good way by the fact that it's also going to implicitly capture what the previous months imply for the last month of the quarter, say, or the missing months of the quarter, but also because we're using fully real-time data for any, you know, striking revisions property. So say in the limiting case, if you've got data up to January and you want to forecast Q1, and you know that the January data gets revised so much that it's useless, then you'd expect this model to just put 0 weight on that lag and kind of put more weight on the previous lags.
Andre, can I just give you a 5-minute warning?
Yes, thanks for that.
Yes.
I think it's just, it's actually 3, but I won't take very long, thank you. So the other element of the model is how the surveys. So making the opposite argument that I just made, there the relationship is fuzzier and you don't really need that additional precision. And indeed, if you estimate separate coefficients for each of the lags, you very often very easily end up just in overfitting with weird, you know, negative signs and bouncy coefficients that don't really make sense. And if you test them out of sample, they don't help in terms of your forecasting ability. So keeping the model parsimonious in that bit, in that particular bit is useful. The one thing that I've left to mention in terms of the specification is, well, but you don't just have one survey, and you don't want to include 1 million lags of 3 different surveys or more in the same regression. So how can you exploit that sort of information when you've got a number of different indicators that are all good, but you can't include them in the same regression? And you know, there's more than one answer to this, but the way that we do it is just by resorting to forecast averaging. So we essentially estimate this same regression here in this example 3 times, always with the monthly GDP lags here and with the lags of each survey in each of the regressions. And then we just take an average, and again, many possibilities, but we found that a good performing one is based on the on discounted inverse RMSE. So it essentially penalizes recent errors more, and that works well in practice. So I'll probably need just a couple more minutes, if that's okay, to show you the results. So how does it do in practice? So what happens is you can retrieve the approximate weights in a roundabout way that the model is putting on monthly GDP versus the surveys. And this is the picture that you get. So early on in the quarter, the surveys in pink are much more informative than monthly GDP. That's because monthly GDP is too volatile. So whatever happened 5 months ago tells you nothing about what's going to happen in the most recent months, in a sense. But as you go along, you get the first month of monthly GDP, and the model recognizes that, you start filling in the gaps. You've got 4 months out of the 6, and the mechanical relationship starts to kick in. But it's only when you get to the second month of monthly GDP, then you see this radical shift where the model just puts 98% or whatever that number is on the monthly GDP data. That's just because whatever the surveys might be telling you, you've got 5 out of 6 months. So there's really not that much margin for things to change. And I just showed you that, the last month, all else equal, is the one that matters least anyway. So you can see that in practice if I show you just 3 snapshots of the model's out of sample performance at different points of the data cycle. So this is at the very start when the previous quarter's quarterly GDP gets released. So you kind of see, it tracks the broad trend. It even kind of anticipates some of the spikes here, and that's because the lagged monthly GDP data from the previous quarter, it captures some of the base effects there. But of course, there's still some very large errors. UK GDP has quite a bit of volatility to it. Then you get another month of monthly GDP, and you see that you get quite a lot closer in many cases. If I flick back and forth, and you really start to pin down many of these volatile moves. And as I say, that's reflecting the fact that month 1 is really important for the quarterly growth rate, conditional on your base effect and all that. But here's what you get once you incorporate month 2 into the model, and this is all out of sample, as I said. So you pretty much nail GDP almost every single time, as you should, because you've got 5 out of 6 months. So it's just getting a specification that allows you to capture that. The only times that you don't is when something crazy happens in month 3. So that's the 2010 snow, and this here is some I forget the exact timing, but it's Jubilee Olympics distortions as well in June of 2012. So that's what you get. And I was just going to make a couple more quick points, which is you can compare this full model just to get a sense of, is it doing what we want it to do and what we think it's doing? The root mean squared error of the model through the data cycle. And you can compare that one to just your standard AR1 benchmark, and it beats that easily. But it also beats, the 2 nested versions from that specification if you just use the lags of the surveys, or if you just use the lags of GDP. And you can see here that, the surveys alone perform relatively well at the start of the quarter, but then don't really add much value beyond that. So it's as good as it gets. Whereas if you just relied on the GDP data, you do quite poorly at the start, but towards the end, the mechanical relationship kicks in and allows you to get very close. So what the full model does is sort of getting the best of both worlds by shifting the weight between one and the other as you go along. I'll probably skip this one, but the point is that you can also, besides the limiting cases of the nested versions, you can also try any linear combination of just surveys, just monthly GDP, and the full model always beats that, or does at least as well. So to the extent that you believe MIDAS is a good way of exploiting information in the surveys, and it's also a good way of exploiting the information in monthly GDP, then this particular hybrid specification pretty much does as well as possible at all points in the quarter, is what this chart suggests. So I'll skip that one just to say, it still it does manage to react quite sharply to the GDP news under COVID. So it's sort of robust to that, if not 100%, but we can discuss that later if people are interested. I'll stop there. So a good way, I think, to exploit these 2 key bits of information, monthly GDP versus surveys. It teaches us about what data are useful when. Surveys are useful early on. Official data is most useful later in the quarter. That's very much in line with our practical experience. And it's a framework that you can apply to a broad range of variables. So hopefully it can be helpful to others. And sorry that I've overrun so much. Questions, please.
Thanks. So you have a question from Anna?
Yeah. Hi. Something I didn't get it for sure is that have you did you impose the aggregation weights or not?
No, nothing is imposed. It's all estimated. Which do you mean the time aggregation?
This one, this 1/3, 2/3 one, because
No. This here is theoretically, these are the weights. The model is not constrained in any way to conform to this, but in practice, it is able to retrieve something very close to this. And that's why it then is able to pin down quarterly GDP so well, because it just fills in the blanks for the 5 first months. You're only missing a tiny.
Something I would do here is to change the left-hand side variable to be just the additional GDP that you don't know so far. So based on your results, you have these very good results. That's once you have all the months that you need, all the 6, right? Actually 5 growth rates to compute the quarterly aggregate. You're very near to the quarterly aggregate, right? So yes. What I would do is that for each month, I would change the left-hand side variable to just put the part that's new and impose the aggregation weights on the past data. We can talk if you want more about this later. I have an older paper that I did that way, but that these weights were imposed because the idea is just what you said. If you had all the months of monthly GDP, you have the first release of GDP. So over time, basically, you just need to forecast, 1 out 5 or 2 out 5, depending where you are in the cycle.
Yeah, that's we should certainly discuss. One reason why, so you could certainly do that. One reason why it may be helpful still to have the quarterly on the left-hand side is that implicitly, the model is also forecasting revisions implicitly. I can't tell you what they are, what I mean. But the fact that I'm throwing in the real-time data on the right-hand side, as I said, if your latest,
so you don't use only the first release on the left-hand side.
Sorry, I use only the first estimate on the left-hand side, but the right-hand side are, if you've only got data to January, it's whatever the time series was at that time, January, December, and so on. But then as you go from January to February, the ONS publishes a new data point. January, December, and so on get revised as well. Mm-hmm. So you kind of want to try to account for, to downweight the data to the extent that it tends to get revised. And the quarterly to monthly specification allows you to account for that as well. So that's one thing that I didn't want to do. I didn't want to impose the mechanical weights because there are reasons why you might want to deviate from that. If you don't fully believe the monthly data is a good reason to deviate from it. And I want to leave that up to the model to decide whether or not it's the case. But we can discuss later. I don't know if there are other questions.
Yeah, I just sent you the link.
Thanks. I have one question regarding the weight. So if you don't impose the weight, then for instance, if the recessions usually happen in the last month of the quarter, you will capture that in your weight. But if the recession suddenly starts in the beginning of the quarter, then because you do not impose the weight, you might miss it, I think.
Absolutely, yeah. So I skipped that chart, but that's exactly what this COVID chart here shows. So here's the 3 versions of the model, full and the 2 nested one, monthly GDP one, and surveys only, during COVID. And what you see is the full model doesn't take the April massive 20% fall in GDP at face value because the surveys don't give quite the same signal for technical reasons. They don't go deep enough. Whereas if you only took the GDP data, then you kind of go down towards where you should be. You take that data at face value. So it's always important to kind of think through what's the right specification to use at different points in time. So that just speaks to my previous point that informing your modeling choices based on the properties of the data and what you know about what's currently happening is crucial as well. I hope that answers your question.
Right, thank you. Thanks for everyone for participating.